Welcome to YU. So far, we have studied systems of linear equations which have single unique solutions, infinitely many solutions, or no solutions. And we have seen that when those systems are represented as augmented matrices, it is easy to tell which type of solutions the system has once the matrix has been transformed to reduced row echelon form through the process of Gauss-Jordan elimination. In three-variable systems, we have also seen how the planes which graphically represent those equations change during that process when the system has a single unique solution or infinitely many solutions. But we have not yet seen how the planes change when a system has no solutions. Systems of linear equations with no solutions are called inconsistent since no variable values exist that are consistent with the solutions for every equation in the system. In the previous lecture, we saw that when a matrix representing an inconsistent system is reduced using Gauss-Jordan elimination, at some point during the process, a row will be produced with all zero coefficient entries and a non-zero constant entry. In this lecture, we will examine different ways that a system of linear equations in three variables can be inconsistent and how the planes which graphically represent this system change during the process of Gauss-Jordan elimination. We have seen that any system whose graph contains two distinct parallel planes will be inconsistent, since distinct parallel planes have no points in common, and therefore the equations which those planes represent can have no common solutions. Regardless of the orientation of the other planes in the system, no point can exist which simultaneously lies on all planes. Another configuration which produces an inconsistent system is a system containing a group of three planes which are not parallel, but whose intersections lie along three parallel lines. Since in this configuration no point can simultaneously lie on all three planes, the system has no solutions and is therefore inconsistent. We will refer to this configuration of planes as a triangular tube. No matter how many equations and planes are included in a system, as long as any two of the planes are parallel, or any three planes form a triangular tube, it is impossible for a point to simultaneously lie on every plane in the system, and so the system will have no solutions. So let's see what happens to these parallel planes and triangular tubes when Gauss-Jordan elimination reduces an inconsistent system in three variables. Before we start, it is useful to know that equations representing parallel planes can often be spotted without having to go through the process of Gauss-Jordan elimination. If this is the case, we can save a lot of time, since we know that the system has no solutions. As an example, let's take a very simple system of two parallel planes. Notice that both equations have the same x coefficient of 1, but the constants in the equations are different. Now let's make the equations a bit more complicated by adding a y term. These equations still describe parallel planes, and just as before, the variable coefficients are the same in both equations, while the constants are different. In fact, any two equations whose coefficients are the same but whose constants are different will describe parallel planes. Now let's change the second equation by multiplying it by 2. Since multiplying both sides of an equation by a non-zero constant doesn't change its solutions, the two equations still describe the same planes. This might make the situation a little less obvious. However, if we notice that the coefficients in the second equation are all twice the value of the coefficients in the first equation, but the constants are not, we could still recognize that the equations describe parallel planes. So when the coefficients of two equations in the system are the same multiple of each other and the constants are not, this tells us that the system is inconsistent. Likewise, if we also multiply the first equation by 3, the coefficients in the second equation are all 2/3 of the coefficients in the first equation, and the constants are not. So once again, this indicates an inconsistent system, but now this relationship between the two equations is even less obvious. Fortunately, even if we don't notice that two equations in the system describe parallel planes, Gauss-Jordan elimination will take care of this for us. So let's see what happens when we represent the system in matrix form and use Gauss-Jordan elimination to convert the system to reduced row echelon form. We start by changing the leading entry of the first row to a 1 using a scale operation to multiply row 1 by 1/6. We then change the entry below that 1 to a 0 using a pivot operation, adding -4 times row 1 to row 2. This changes all the coefficient entries in row 2 to 0, but not the constant entry. At this point, we can stop, since we know that the system has no solutions. Or if we like, we can continue the process of Gauss-Jordan elimination until the matrix is in reduced row echelon form. To do this, we must change the leading entry of row 2 to a 1 using a scale operation to multiply row 2 by -1/40. And since each leading entry must be the only non-zero entry in its column, the entry above that leading entry must be zeroed using a pivot to add -6 times row 2 to row 1. Since every row's leading entry is a 1 positioned to the right of the leading entry above, and every leading entry is the only non-zero entry in its column, the matrix is now in reduced row echelon form. So if a system contains parallel planes, during the process of Gauss-Jordan elimination, a row of all zero coefficient entries with a non-zero constant entry will be produced, indicating that the system is inconsistent. But as we have seen, parallel planes are not the only configuration which can cause a system to be inconsistent. 3 planes forming a triangular tube will also create an inconsistent system. So how do we recognize this type of system? Unfortunately, a system of equations whose graph contains a triangular tube cannot typically be spotted by simply looking at the equations. If this system, represented in matrix form, is reduced through Gauss-Jordan elimination, what sort of indication of inconsistency will be produced? To find out, let's reduce this matrix. We start by changing the first row's leading entry to a 1, using a scale operation to multiply row 1 by 1/4. We then change the entry below the 1 to a 0, using a pivot operation to add -12 times row 1 to row 2. The bottom entry in that column is then changed to a 0, using another pivot operation to add -12 times row 1 to row 3. We then change the leading entry of row 2 to a 1, using a scale operation to multiply row 2 by 1/16. And the entry below that is then zeroed, using another pivot operation, a constant entry, indicating that this system is inconsistent. At this point, we can stop since we know that the system has no solutions, or we can continue until the matrix is in reduced row echelon form. To do this, we change the leading entry of row 3 to a 1, using a scale operation to multiply row row 3 by negative 1/32. The leading entries of each row are now 1s, but to be in reduced row echelon form, each leading entry must be the only non-zero entry in its column. We therefore must zero the entries above the leading entry of row 3 and row 2. We start by zeroing the entry above the leading entry of row 3, using a pivot to add negative 5/2 times row 3 to row 2, pivot to add 3 above the leading entry of row 2, using a pivot to add row 2 to row 1. Since every row's leading entry is a 1, positioned to the right of the leading entry above, and every leading entry is the only non-zero entry in its column, the matrix is now in reduced row echelon form. So just as in the previous example, Gauss-Jordan elimination produced a matrix row containing all zero coefficient entries with a non-zero constant entry. But considering that this system contained no parallel planes, how did we end up with the same type of result as the system which contained parallel planes? Surprisingly, during the process of Gauss-Jordan elimination, two of the planes in the system became parallel. So why did the planes described by rows 2 and 3 become parallel? When Gauss-Jordan elimination reduces a matrix representing equations which describe a triangular tube, during the reduction process, coefficients of the same variable will be zeroed in two of the equations, causing the corresponding planes to become parallel to the same coordinate axis. In this example, the zeroed coefficient entries were in the x column, so the corresponding planes each rotated around their parallel lines of intersection with plane 1, becoming parallel to the x-axis and therefore parallel to each other. Then, just as in any system containing parallel planes, a pivot operation acting on rows corresponding to the parallel planes produces a row of all zero coefficient entries and a non-zero constant entry, indicating that the system is inconsistent. So far, we have seen two configurations of planes that will produce an inconsistent system of three linear equations in three variables. However, in three-variable systems with more than three equations, there are additional configurations that produce inconsistent systems which don't contain parallel planes or triangular tubes. But in all cases, at some point during the process of Gauss-Jordan elimination, an equivalent system with parallel planes will always be produced, resulting in an indication of inconsistency. One quick example will show how this happens. Consider a system containing the equations x equals 0, y equals 0, and z equals 0. This system has a single unique solution corresponding to the common point at the origin shared by all three planes. Now let's add a fourth equation, x plus y plus z equals 3. Since this fourth plane does not include the single point shared by the other three planes, there is no point common to all four planes. This system is therefore inconsistent even though it contains no parallel planes or triangular tubes. Now let's see what happens when we use Gauss-Jordan elimination to reduce this system. Since the leading entry of the first row is already a 1, we only need to zero the other non-zero entry in that column to row 4. Since the x coefficient of row 4 is now 0, this causes plane 4 to become parallel to the x-axis. The leading entry of the second row is also already a 1, so we only have to zero the other non-zero entry in that column. Adding -1 times row 2 to row 4. Since the y coefficient of row 4 is now 0, this causes plane 4 to also become parallel to the y-axis. Since plane 4 is now parallel to the x and y axes, it has become horizontal, so planes 3 and 4 are Gauss-Jordan, adding -1 times produced when a pivot acts on two matrix rows corresponding to parallel planes. A row containing all zero coefficient entries and a non-zero constant entry, indicating an inconsistent system. In the last several lectures, we have seen how systems of linear equations can be solved using matrices and the process of Gauss-Jordan elimination. This technique is especially useful in systems of more than 3 variables, where the substitution or elimination methods can become cumbersome. But what type of actual applications can be solved by systems of linear equations with more than 3 variables? In the next several lectures, we will take a look at some real-world applications which can be modeled by systems of linear equations with 4 or more variables.